Welcome back. In this lecture, we will learn the inductor power loss. From previous lectures, we already know that an inductor consists of winding, magnetic core, and air gap. Among these three major components, power loss is primarily associated with the winding and magnetic core. Let's focus on these two items that contribute to the major power loss. In the real world, there must be some power loss associated with the inductor. Power is dissipated as heat within the inductor, resulting in an increase in the temperature. Large temperature rise will have several detrimental effects on the inductor, such as resistance increase, core saturation, wire insulation damage, and mechanical stress. Power loss hurts the system efficiency, challenges the thermal management, and affects the overall system reliability. Therefore, it's important for us to have a fundamental understanding of inductor power loss. Generally speaking, there are two types of power loss associated with inductors. Power loss in the winding is called copper loss, or abbreviated as PCU, where Cu stands for copper. Power loss in the core is called core loss, or abbreviated as PFE. Fe stands for farad. Firstly, we will learn the inductor copper loss in this lecture. In the next lecture, we will learn the core loss. Let's start with basic concepts of copper loss in this lecture. According to the operating frequency, we can put them in two categories: low frequency copper loss and high frequency copper loss. Let's talk about low frequency copper loss first. Low frequency copper loss is caused by the DC current, or DC, resistance in the winding. DC resistance is the resistance under a DC or low frequency current. It is often called RDC or DCR. In the illustration, we have a piece of winding conductor with a bare cross-sectional area AW, the length L, and the current I. The current density J of D is defined as current I of T over cross-sectional area AW. Current density can be plotted as a flat line over the distance d. That means the current density is constant over the diameter. In other words, all materials of the winding is well utilized to carry the current. Total resistance R is defined as the resistivity ρ times L over AW. Ρ is the resistivity. The copper loss PCU is defined as R mass current squared times R. For example, the resistivity of soft annealed copper wire is about 1.724 times 10 to the power of minus 6 ohm centimeter at 25 degrees C. At 100 degrees C, the resistivity is increased to 2.3 times 10 to the power of minus 6 ohm centimeter. That means the low frequency copper loss will increase as temperature rises up. Next, we will learn about high frequency copper loss. Before we go to the details of the high frequency copper loss, here are a few questions for you. Why do we care about high frequency? Where does the high frequency current come from? What is the high frequency effect on copper loss? Please pause the video and think about these questions. To answer these questions, let's take a look at a buck converter that we have seen before. Again, a buck converter is a switch mode power supply that converts the input voltage to an output voltage with a lower magnitude. The current is flowing through the inductor from input to the output. The switch node on the left terminal of the inductor is a high-frequency switching network, which can be either connected to terminal 1 or 2 at the switching frequency, for example, a few hundreds of kilohertz. The switch node voltage is illustrated as VSW over T. For example, the switch is at node 1, switch voltage equals to input voltage Vin, and the time duration is T on. Positive voltage of Vin minus Vout is applied across the inductor. Therefore, the inductor current rises up at the slope of Vin minus Vout over L. This is a positive slope. When the switch is at node 2 for the rest of the period, VSW equals to 0, which is connected to ground, and the time duration is T off. T on plus T off is the whole period. During T off, the negative voltage minus V out is applied at the inductor, and hence the inductor current falls down with a negative slope of minus V out over L. Dashed horizontal line indicates the average current of the inductor. We can see the inductor current is changing up and down at the center of the average current. Again, during T on, the current is going up with a positive slope. During T off, the inductor current is decreasing with a negative slope. As we can see here, the inductor current is never a pure DC current. Actually, the inductor current consists of both DC and AC components. People often call this type of AC current as ripple current. In this ideal buck converter, the ripple current depends on input voltage, output voltage, and the inductance. Note that at steady state, if the inductor current never goes to zero, it is in the continuous conduction mode, or CCM. In summary, in a switch mode power supply, the high frequency current component comes from the current ripple at the switching frequency. We know that inductor has a high frequency current ripple in a switch mode power supply. Next, we will learn the high frequency copper loss. There are two effects associated with the high frequency current. They are skin effects and proximity effects, which can cause the winding losses to be significantly greater than the DC copper loss. Skin effect occurs in individual wires. Proximity effect occurs in adjacent wires. Both effects are caused by eddy currents, which are induced by the varying magnetic field in the winding. Let's learn about the skin effect, which occurs in individual wires. Skin effect is a tendency of alternating high-frequency currents to crawl towards the surface of a conducting material. It is a phenomenon that occurs in conductors at high frequencies, whereby the majority of the current flows near the surface or skin of the conductor, rather than uniformly throughout its cross-section. For instance, the image illustrates the distribution of alternating current, or AC current, flowing within a cylindrical conductor. We observe that the current density diminishes exponentially from the surface toward the interior. Skin effect in wires reduces the effective cross-sectional area of the conductor. This leads to increased resistance in the conductor at high frequency, which is also known as AC resistance. Therefore, skin effect will lead to extra power loss in the winding. The illustration explains the cause of skin effect. A current I flowing through the conductor introduces a magnetic field H with a magnetic flux density phi. The direction of magnetic flux can be found by the right-hand rule, shown on the right-hand side. According to the Lenz's law, the AC flux in the conductor induces eddy currents, which flow in the manner that tends to oppose the AC flux phi, as shown in purple. The induced eddy currents partially cancel the current flow in the center and reinforce it near the surface, or skin. In this figure, it can be seen that eddy currents tend to reduce the net current density in the center of the conductor, while increase the current density near the surface of the conductor. For this reason, current density decreases exponentially from the surface towards the inside, as shown on the left-hand side, so that the conductor looks like a hollow cylinder at high frequency. To further simplify the analysis, we can assume that the current density is uniformly only at skin penetration depths, defined as delta, and it has no current flowing in the center of the conductor, as shown in this picture in the middle. Symbol delta is defined as the penetration depths or skin depths in the conductor at high frequency applications. The penetration depth of copper conductor is plotted in this figure as a function of frequency f, as in a log-log graph. In this graph, there are two y-axes. The first y-axis on the left shows the penetration depth in centimeters. On the right-hand side, it shows the wire diameter d of standard American wire gauge, AWG. This graph gives you a basic idea about how much cross-sectional you can actually use at a certain frequency. Since effective cross-sectional area is reduced by the skin effect, the overall resistance is increased at AC. The AC resistance due to skin effect is defined as RAC, which is equals to RDC plus delta R, where RDC is the DC resistance, while delta R is the resistance increase due to the skin effect. On the right-hand side, this table provides a ratio of AC resistance RAC to DC resistance RDC at 4 different frequencies from 25 kHz to 200 kHz. This is the commonly used switching frequency for switch mode power supplies. Sine wave and square wave currents are both provided. This table shows as frequency goes up, RAC increases as well. In addition, at the same frequency, the square wave current has more RAC than sine wave, since square wave has higher frequency components than pure sine waves. Here is a quick summary of high-frequency copper loss, PCU. At high frequency, there are eddy currents in the conductor causes the skin effect. The cylindrical conductor becomes hollow. This leads to additional AC resistance and high-frequency copper loss. How to reduce skin effect? There are few examples to reduce skin effects. For example, you can lower the operating frequency and increase the skin depth. Also, you can use a conductor with lower magnetic permeability. This will minimize the large magnetic field across a conductor. Another good solution is to use stranded wires instead of solid wires. In this slide, it shows a lead wire, which is a good solution to carry high-frequency current. It is often used in windings of high-frequency transformers to increase their efficiency by mitigating both skin effect and proximity effect. As you can see here, this bundle has multiple insulated strands to increase the effective cross-sectional area. One application of eddy current is the induction heating. Induction heating is a process of heating an electrical conducting object, usually a metal, by electromagnetic induction, where eddy currents are generated within metal, so there are a few advantages. For example, the heat is only generated inside the object itself. These objects can be heated very rapidly. There is no external contact, which can be important where contamination is an issue. Now let's watch a video to show the induction heating. You can see the heat is quickly generated inside this object, and there's no external contacts or external heat source. Next, we will learn about proximity effect, which happens in adjacent wires. This is the first case. There's only one conductor is carrying an AC current. The proximity effect is another phenomenon that occurs in conductors carrying AC current, particularly at high frequencies. Unlike the skin effect, which affects the distribution of current across the cross-section of a single conductor, the proximity effect is concerned with the interaction between adjacent conductors or parallel paths carrying AC currents. The illustration shows the case 1 that has only one conductor carrying a current, and conductor number 2 is open circuit. The AC current I causes a large primary magnetic field changing over the conductor number 2. According to the Lenz's law, the eddy current are generated inside the conductor 2 to create a secondary magnetic field, which will cancel out the primary magnetic field created by conductor 1. Therefore, there are power loss associated with the proximity effect in conductor 2 due to eddy currents. The second case of proximity effects involves with two adjacent conductors that are both carrying current. If the currents are in the same direction, the proximity effect causes the current to concentrate to the side away from the nearby conductor, as shown in this picture on the left. If the AC current are in the opposite directions, the proximity effect causes the current to concentrate on the side adjacent to the nearby conductor. Proximity and skin effects increase power losses in transformers and inductors operating at high frequencies, which are usually used in switch mode power supplies. Note that RAC loss is not included in the inductor realistic model. Recap: in this lecture, we learned power loss in an inductor consists of copper loss and core loss. Copper loss in windings can be divided into low frequency and high frequency copper loss. High frequency copper loss can be caused by skin effect and proximity effect. In the next lecture, we will learn about core loss. Here's a reference for this lecture. Thank you and see you next time.